Hi, welcome back to our video on the immersed pipe flow with an orifice plate. Alright, in this video we want to continue the analysis, and in the last video we actually derived this equation for the pressure drop across the orifice, or rather across this little red box here, this control volume. And now our next step is actually, okay, since we actually derive the pressure drop here, and we want to find the pressure drop from here to here, the next thing we need to do is derive the pressure drop from here. Sorry, we don't have to derive anymore. We already derived the pressure drop from here to here and here to here. So since we want to find the pressure drop from here to here, we just add the pressure drops here up. What we do is we substitute back our expression from the Bernoulli's equation earlier to find the pressure drop in this little black box here, from here to here. That's our expression there. And now we add these pressure drops up. We add these two equations up and we will get this. Now this is just the first part of when we copy this part down. We add it to this expression here. Vc times 1 minus AC over 0.63 times of A orifice. Oh, this Vc is squared, sorry. So that's what we are doing here. We are adding these two equations up. We get this because PVC and minus PVC actually cancel out. So this is just the pressure drop from PC to P infinity. So here it is, one here and here. And here we are just doing a little bit more math to simplify this equation. Because this is when we multiply half times of VC out, or you just multiply things out by the factor of half to get this. Inside we need to multiply it 2 times. Alright? So when we simplify this equation here, we will then get this minus 1 plus 2, and here is the minus 2 we had earlier. Alright, minus 1 plus 2, and this part here, it will be truncated into this form, and it can be further truncated into this form. Alright, because you see this is a squared plus b squared minus 2ab. You can just truncate it into this form. The next thing we want to find out is how it actually relates to our free stream pressures and free stream velocity. Now, we said earlier that we can neglect the head loss of the streams flowing from here to here. So normally that is not the case, simply because when we enter from the free stream into the pipe, the velocity actually slows down. The fluid actually undergoes some kind of expansion, and in terms of momentum you can think of it as an inelastic collision where there is some losses down here. Now of course we assume that's negligible, that's why we can use the Bernoulli's equation right over here. So assuming it's a horizontal flow, P infinity, the free stream pressure over the density of the fluid plus the kinetic energy per unit mass, alright, that will equal the pressure in here, the pressure energy, plus the kinetic energy in here, kinetic energy term. And what is this term here? This term here is basically this term. But how do we get this? We actually take the P infinity minus rho over to the other side here. Alright, so just shifting it from here to here, and then we get this equation. Now we have this, we know this, we substitute this entire expression into this. Alright, so I haven't finished writing. Just need to complete it. This and this expression here plus P, the free stream pressure over rho, plus Vc squared over 2 okay, and that will equals to P infinity over rho plus U infinity squared over 2. Now immediately we can see some terms start to cancel. That is a good thing for your calculations. It really simplifies a lot of things. So next we have U infinity squared over 2 equals to half Vc squared. Minus 1 squared plus Vc over 2 squared. Ah yes, this is the good news. We have all these, what do you call that? We have all these knowns. This is known and this is known. And we can see the only unknown will be Vc, which is what we actually wanted to find out in the first place. It's been very long, a very long derivation, but at least we had progress here. So this is just U infinity squared over 2 Vc squared, U infinity squared over 2, the free stream velocity squared over 2 equals half times Vc squared AC over 0.63 Orifice minus 1 squared. And that plus half. Oh, the half isn't there. It's just plus 1. And that is our expression for Vc. Now we want an expression for Vc. We just cancel these terms out. And we square root both sides. Now once we square root both sides, and you can find that Vc is just U infinity times 1 over the root of whatever this thing is here. I want to read that out. This should be a plus 1. Okay. Let's just tidy this up. There you go. Very nice little neat expression there. Compared to all the mess that we've been through, it's pretty rewarding. But alright, we find out that this is known, and this is known. Everything else is known. It's just this is unknown. So now this is known because we know everything on the right hand side. So coming back to our question, we wanted to find the volumetric flow rate in there, Q. So that is just AC times Vc. So that is just U, the free stream velocity times AC over whatever this mess is in here. There you go. And that is our answer for this question. So let's see, does it make sense? We can see that, okay, if my area inside the pipe is bigger, if I enlarge this area, obviously the volumetric flow rate inside the pipe will be larger, right? And if the free stream velocity inside is bigger, obviously this will become bigger as well. Now, another interesting observation is that if there was no orifice in there, the vena contractor area will just be AC, and this entire term will be 1. Extreme case. Let's see again. This is just 1 minus 1, that's 0. The extreme case, no orifice. And this is just a little extra for your information. U infinity AC over root 0 plus 1. What's the root of 1? That's just 1. So in terms of magnitude, it's just U infinity times AC, which makes perfect sense for us. Now imagine if A orifice is just 0 because the whole thing is closed. Alright, now what happens? If A orifice is 0, this entire term here will become infinite or undefined. So whatever's inside this square root is undefined and infinitely big. And once that happens, this number divided by an infinitely big number just becomes 0. There's no flow rate at all. So for an orifice with 0 area, which is just a plate there, there's no hole or anything, there's no flow. And therefore this equation kind of makes sense for us. Yeah? And the bigger the orifice area, the larger the flow rate. So that's what this equation is telling us. Okay, thanks for watching. I hope you have found this video useful in your analysis of fluid flows. If there are any questions or comments, please post it in the comment section below. Thanks for watching. And please subscribe if you find it useful for yourself. Thank you very much.